हाय एवरीवन, दिस इज़ धीरज गोरे। आई होप आप लाइफ में बढ़िया कर रहे होंगे। तो आज हम करने वाले हैं चैप्टर 5 कोऑर्डिनेशन कंपाउंड्स क्लास 12 केमिस्ट्री का। तो चलिए स्टार्ट करते हैं। कोऑर्डिनेशन कंपाउंड्स आर द बैकबोन ऑफ मॉडर्न इनऑर्गेनिक एंड बायो इनऑर्गेनिक केमिस्ट्री एंड केमिकल इंडस्ट्री. In the previous unit, we learned that transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital compounds of biological systems. Chlorophyll, hemoglobin, and vitamin B12 are coordination compounds of magnesium, iron, and cobalt, respectively. Variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Coordination compounds are also find many applications in electroplating, textile dyeing, medicinal chemistry. 5.1 Werner's theory of coordination compounds. Alfred Werner, 1866 to 1919, a Swiss chemist, was first to formulate his idea about the structure of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of primary valence and secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl2, or PdCl2 have primary valence 3, 2, and 2 respectively. In a series of compounds of cobalt 3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remain in the solution. 1 mole of copper Cl3.6 NH3 yellow gave 3 mole AgCl. 1 mole CoCl3 5 NH3 purple gave 2 mole AgCl. 1 mole CoCl3.4 NH3 green gave 1 mole AgCl. 1 mole CoCl3.4 NH3 violet gave 1 mole AgCl. This observation, together with the result of conductivity measurements in solution, can be explained if 6 groups in all, either chloride ions or ammonia molecules or both, remain to the cobalt in ion during reaction. Second, the coordination are formulated as shown in table 5.1, where the atoms within the square brackets form a single entity which does not dissociate under the reaction condition. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valences are 6. Formulation of cobalt 3 chloride ammonia complexes. Table 5.1. Note that the last two compounds in table 5.1 have identical empirical formula CoCl3.4 NH3 but distinct properties. Such compounds are termed as isomers. Werner in 1998 propounded his theory of coordination compounds. The main postulates are: in coordination compounds, metals show two types of linkages, valencies, primary and secondary. The primary valencies are normally ionizable and are satisfied by negative ions. The secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. The ion groups bound by the secondary linkages to the metal have characteristic spatial arrangement corresponding to different coordination numbers. In modern formulation, such spatial arrangements are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. He further postulated the octahedral, tetrahedral, and square planar geometrical shapes or common in coordination compounds of transition metals. Thus, copper NH3 whole 6 3 plus, CoCl NH3 whole 5 2 plus, and CoCl2 NH3 whole 4 plus are octahedral entities, while NiCO whole 4 and PtC4 hole 2 minus are tetrahedral and square planar respectively. Difference between a double salt and a complex salt. Both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts such as carnallite KCl.MgCl2.6H2O, Mohr salt FeSO4.NH4 whole twice SO4.6H2O, potassium Kl SO4 whole twice dot 12H2O, etc. dissociate into simple ions completely, then dissolved in water. However, complex ions such as FeCN whole 6 power 4 minus of K4 FeCN6 do not dissociate into Fe2 plus and Cn minus ions. Werner was born on December 12, 1866 in Mulhouse, a small community in French province of Alsace. His study of chemistry began in Karlsruhe, Germany, and continued Zurich, Switzerland, where in his doctoral thesis in 1890 he explained the difference in properties of certain nitrogen-containing organic substances on the basis of isomerism. He extended what Von Half theory of tetrahedral carbon atom and modified it for nitrogen. Werner showed optical and electrical differences between complex compounds based on physical measurements. In fact, Werner was the first to discover optical activity in certain coordination compounds. He, at the age of 29 years, became a full professional at Technische Hochschule in Zurich in 1895. Alfred Werner was a chemist and educationalist. His accomplishment included the development of the theory of coordination compounds. This theory, in which Werner proposed revolutionary ideas about how atoms and molecules are linked together, was promulgated in a span of only 3 years, from 1890 to 1893. The remainder of his career was spent gathering the experimental support required to validate his new ideas. Werner became the first Swiss chemist to win the Nobel Prize in 1913 for his work on the linkage of atoms and the coordination theory. 5.2. The definition of some important terms pertaining to coordination compounds. A. Coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, COCl3 NH3 whole thrice is a coordination entity in which cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO whole 4, PtCl2, NH3 whole twice, FeCN whole 6, 4 minus, CONH3 whole 6, 3 plus. B. Central atom ion. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. For example, the central atom ion in the coordination entities NiCl2 H2O whole 4, COCl NH3 whole 5 2 plus and FeCN6 whole power 3 minus are Ni2 plus and CO3 plus and Fe3 plus respectively. These central atoms or ions are also referred to as Lewis acids, ligands. The ions or molecules bound to the central atom or ion coordination entity are called ligands. These may be simple ions such as Cl minus, small molecules such as H2O or NH3, larger molecules such as NH2, CH2, CH2, NH2, or N in bracket CH2, CH2, NH2 thrice, or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with Cl minus, H2O or NH3, the ligand is said to be unidentate. when a ligand can bind through two donor atoms as H2N, CH2, CH2, NH2, ethane 1,2 diamine, C2O4 2 minus oxalate. The ligand is said to be didentate when several donor atoms are present in a single ligand, as in CH2, CH2, NH2 whole thrice. The ligand is said to be polydentate. Ethylene diamine tetraacetate ion, also known as EDTA 4 minus, is an important hexadentate ligand. It can bind through two nitrogen and 4 oxygen atom to a central ion. When a di or polydentate ligand uses its two or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called denticity of ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidentate ligands. Ligand which has two different donor atoms, either of the two ligands in the complex, is called ambidentate ligand. Example of such ligands are Na2 minus and Cn minus ions. Na2 ions can coordinate either through nitrogen or through oxygen to a central metal atom or ion. Similarly, Cn ion can coordinate through the sulfur or nitrogen atom. D. Coordination number. The coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions PtCl6 2 minus and NiNH3 4 whole 4 2 plus, the coordination number of Pt and Ni are 6 and 4 respectively. Similarly, in the complex ion Fe in bracket C2O4 whole thrice 3 minus and CONe En whole thrice 3 plus, the coordination number of both Fe and CO is 6 because C2O4 2 minus and ethane 1,2 diamine are didentate ligands. It is important to note here that coordination number of the central atom or ion is determined only by the number of sigma bonds formed by the ligand with the central atom or ion. pi bonds, if found between ligand and the central atom ion, are not counted for this purpose. E. Coordination sphere. The central atom ion and the ligand attached to it are enclosed in square bracket and is collectively termed as coordination sphere. The ionizable groups are written outside the bracket and are called counterions. For example, in the complex K4 FeCN6, the coordination sphere is FeCN whole 6 4 minus and the counterion is K plus. F. Coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedra about the central atom. The most common coordination polyhedra are octahedral, square planar and tetrahedral. For example, CO NH3 whole 6 3 plus is octahedral, NaCO whole 4 is tetrahedral, and PtCl4 whole twice 2 minus is square planar. Figure 5.1 shows the shapes of the different coordination polyhedra. First is octahedral, second one is tetrahedral, third one is square planar, and fourth one is trigonal bipyramidal, and fifth one is square pyramidal. G. Oxidation number of central atom. The oxidation number of central atom is complex is defined as the charge it would carry if all the ligands are removed, along with the electron pairs that are shared with the central atom. The coordination number is represented by a Roman numeral in parentheses following the name of the coordination entity. For example, oxidation number of copper. Copper is +1 as it is written as copper 1. H. Homoleptic and heteroleptic complexes. The complexes in which a metal is bound to only one kind of donor groups. Example: CO1H3 whole 6 3 plus are known as homoleptic complexes in which a metal is bound to more than one kind of donor groups. Example: CO1H3 Cl2 are known as heteroleptic. Nomenclature of coordination compounds. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. The formulas and names adopted for coordination entities are based on recommendation of International Union of Pure and Applied Chemistry (IUPAC). 5.3.1 The formula of a compound is shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single metal atom. The following rules are applied while writing the formulas. First, the central atom is listed first. Second, the ligands are then listed in alphabetical order. The placement of a ligand in which does not depend on its charge. Third, polydendral ligands are also listed alphabetically. In case of abbreviated ligand, the first letter to the abbreviation is used to determine the position of the ligand in the alphabetical order. Fourth, the formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. Fifth, there should be no space between the ligands and the metal within the coordination sphere. Sixth, when the formula of a charged coordination entity is to be written without of that of counterion, the charge is indicated outside the square bracket as a right superscript with the number before the sign. For example, COCN6 3 minus and CrH2O whole 6 3 plus, etc. The charge of the cations is balanced by the charge of the anions. 5.3.2 Naming of mononuclear coordination compounds. The names of coordination compounds are derived by the following principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. First, the cation is named first in both positively and negatively charged coordination entities. Second, the ligands are named in the alphabetical order before the name of the central atom ion. This procedure is reversed from writing formula. Name of the anionic ligands end in O. Those of neutral and cationic ligands are the same except aqua for H2O, amine for NH3 and carbonyl for CO and nitrosyl for NO. While writing the formula of coordination entity, they are enclosed in brackets. Prefixes. Mono, di, tri, tetra are used to indicate the number of individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the terms base, tris, tetra, case are used. The ligand to which they prefer being placed in parentheses. For example, NaCl2 PPH3 2 is named as dichlorobis triphenyl phosphine and nickel 2. Oxidation state of metal in which cation and anion or neutral coordination entity is indicated by Roman numeral in parentheses. If the complex ion is a cation, the metal is named same as element. For example, in a complex cation is called cobalt and Pt is called platinum. If the complex's ion is an ion, the name of the metal ends with suffix 8. For example, CO in a complex anion. CO is Cn4, 2 minus is cobaltate. For example, metal, the Latin names are used in complex anions. Example, ferrate for Fa. 7. The neutral complex molecule is named similar to that of the complex cation. The following examples illustrate the nomenclature of coordination compounds. CrNH3 whole thrice H2O whole thrice. Uh, Outside the bracket Cl3 is named as triamine triaqua chromium third chloride. Explanation: the complex ion is inside the square bracket, which is a cation. The amine ligand are named before the aqua ligands according to the alphabetical order. Since there are 3 chloride ions in the compound, the charge of the complex ion must be +3. Since the compound is electrically neutral from the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecules. Therefore, the oxidation number of chromium must be same as the charge of complex ion, that is +3. Second, CO in bracket H2NN CH2 NH2 whole thrice Cl2. SO4 is named as trice ethane 1,2 diamine cobalt 3 sulfate. Explanation: the sulfate is the counter ion in this molecule since it takes 3 sulfates to bond with 2 complex cations. The charge on the each complex cation must be +3. Further, ethane 1,2 diamine is a neutral molecule, so the oxidation number of cobalt in the complex ion must be +3. Remember that you never have to indicate the number of cations and anions in the name of ionic compound. AgNH3 whole twice AgCN whole twice is named as diamine silver 1 dicyanoargentate 1. Isomerism in coordination compounds. Isomers are 2 or more compounds that have same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. 2 principal types of isomerisms are known among coordination compounds, each of which can be further subdivided. First, stereoisomerism, geometrical isomerism. Second, optical isomerism. B, structure isomerism. First, linkage isomerism. Second, coordination isomerism. Third, ionism isomerism. Fourth, solvent isomerism. Stereoisomerism have the same chemical formula and chemical bonds but have different spatial arrangements. Structure isomerisms have different bonds. A detailed account for this isomers are given below. Arises in heteroleptic complexes due to different possible geometric arrangement of the ligands. Important examples of this behavior are found with coordination numbers 4 and 6. In a square planar complex of formula mx2l2, x and l are unidentate. The 2 ligands X may be arranged adjacent to each other in a cis isomer or opposite to each other in a trans isomer, as depicted in figure 5.2. Other square planar complexes in the type MAABXL, where ABXL are unidentate, shows 3 isomers, 2 cis and 1 trans. You may attempt to draw this structure. Such isomerism is not possible for a tetrahedral geometry. Behavior is possible in octahedral complexes of formula mx2l4, in which 2 ligands X may be oriented cis or trans to each other, figure 5.3. This type of isomerism also arises when didentate ligands LL NH2 CH2 NH2 are present in complexes of formula mx2 LL whole 2. Another type of geometrical isomerisms occur in octahedral coordination entities of the type Ma3B3, like CONH3 whole thrice NO2 whole thrice have 3 donor atoms of the same ligand occupy adjacent position at the corners of an octahedral face. We have the facial isomer, and when the position around the meridian of the octahedron, we get the meridional isomer. 5.4.2 Optical isomerism. Isomers are the mirror images that cannot be superimposed on one another. These are called enantiomers. The molecules or ions that cannot be superimposed are called. The 2 forms are dextro D and levo L. Depending upon the direction they rotate, The plane of polarized light in a polarimetry rotates to the right, L rotates to the left. Optical isomerism is common in octahedral complexes involving identical ligands. In a coordination entity of the type PTCl2 En hold twice, only the cis isomer shows optical activity. Figure 5.7. 5.4.3 Linkage isomerism. Linkage isomerisms arises in a coordination compound containing ambidependent ligand. A simple ligand is provided by the complexes containing thiocyanate ligand NaCS, which may bind through nitrogen to give MnCS or through sulfur to give MsCN. Jorgensen discovered such behavior in the complex CONH3 whole 5 Na2Cl2, which is obtained as the red form, in which the nitrite ligand is bound through oxygen ONO, as the yellow form, in which the nitrite ligand is bound through nitrogen. Coordination isomerism. This type of isomerism arises from interchange of ligands between cationic and anionic entities of different metal ions present in a complex. An example is provided by CONH3 whole 6 CrCN whole 6, in which the NH3 ligands are bound to CO3 plus and the Cn minus ligands to Cr3 plus. In its coordination isomer CrNH3 whole 6 COCN whole 6, the NH3 ligands are bound to Cr3 plus and Cn minus ligands to CO3 plus. 5.4.5 The ionization isomerism. This form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion. An example is provided by the ionization isomer CONH3 whole 5 SO4 Br and CONH3 5 Br and BrSO4. Solvent isomerism. This form of isomerism is known as hydrate isomerism in case where water is involved as a solvent. This is similar to the ionization isomerism. Solvent isomerism differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as phase solvent moleculism. The crystal lattice. An example is provided by the aqua complex CrH2O6 Cl3 violet and its solvent isomerism CrH2O whole 5 Cl2.6H2O gray green. 5.5 Bonding in coordination compounds. Vernon was the first to describe the bonding features in coordination compounds, but his theory could not answer the basic questions like: first, why only certain elements possesses the remarkable property of forming coordination compounds? Second, why the bonds in coordination compounds have directional properties? Third, why the coordination compounds have characteristics, magnetic and optical properties? Many approaches have been put forth to explain the nature of bonding in coordination compounds, with valence bond theory VBT, crystal field theory CFT, ligand field theory LFT, and molecular orbital theory. We shall focus our attention on elementary treatment of the application of VBT and CFT to coordination compounds. Valence bond theory. According to this theory, the metal atom or ion under the influence of ligands can use its n-1d, ns, np or ns, np, nd orbitals for hybridization to yield a set of band orbitals of different geometry such as octahedral, tetrahedral, square planar, and so on. Table 5.2. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for binding. This is illustrated by the following examples. Possibly to predict the geometry of a complex form, the knowledge of its magnetic behavior on the basis of valence bond theory. In diamagnetic octahedral complexes, CONH3 3 plus, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d10. The hybridization scheme is as shown in the diagram. Electrons, one from each NH3 molecule, occupy the 6 hybrid orbitals. Thus, the complex has octahedral geometry as diamagnetic because of the absence of unpaired electron. In the formation of this complex, since the matter inner d orbital 3a 3d is used in hybridization of the complex CO1s3 whole 6 3 plus is called inner orbital or low spin paired complex. The paramagnetic octahedral complex CO uses outer orbital 4d hybridization sp3d2. It is thus outer orbital or high spin or spin free complex. Orbitals of CO ion in a tetrahedral complexes 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. This is illustrated below. NiCl4 2 minus, here nickel plus 2 oxidation state, and the ion has the electronic configuration 3d10 3d8. This hybridization scheme is as shown in diagram. ECl minus ion donates a pair of electrons. The compound is paramagnetic since it contains 2 unpaired electrons. Similarly, NiCO4 has tetrahedral geometry, but it is diamagnetic since nickel is in zero oxidation state and contains no unpaired electron. In the square planar complexes, the hybridization involved is dsp2. An example is Ni and C4 2 minus. Here nickel is in plus 2 oxidation state, has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Orbitals of Na2 plus ion 3d 4s and 4p. dsp2 hybridized orbitals of Na2 plus 3d dsp2 hybrid 4p. Low spin complex 3d 4 pairs of electrons forms 4 cn minus groups 4p. Each of the hybridized orbitals receives a pair of electrons from cyanide ions. The complex compound is dimagnetous as evident from the absence of unpaired electrons. It is important to note that hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. 5.5.2 Magnetic properties of coordination compounds. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiment. The results can be used to obtain information about the number of unpaired electrons and hence structures adopted by metal complexes. A critical study of magnetic data of coordination compounds of metal of the first transition series reveals some complication. For metal ions with up to 3 electrons in the d orbitals like Ti3 plus d1, V3 plus d2, Cr3 plus d3, the 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. The magnetic behavior of this free ion and their coordination entity is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for d4 Cr2 plus Mn3 plus d5 Mn2 plus Fe3 plus d6 Fe2 plus CO3 plus cases, a vacant pair of d orbitals results only by pairing 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. The magnetic data agree with maximum spin pairing in many cases, especially within coordination compounds containing d6 ions. However, with species containing d4 and d5 ions, there are complications. MnCn6 3 minus has magnetic moment of 2 unpaired electrons, while MnCl6 3 minus has a magnetic moment of 2 unpaired electrons, while MnCl6 whole 3 minus has a paramagnetic moment of 4 unpaired electrons. FeCn6 3 minus has a magnetic moment of a single unpaired electron, while FeF6 power 3 minus has a paramagnetic moment of 5 unpaired electrons. COF6 3 minus is a paramagnetic with 4 unpaired electrons, while C2O4 thrice 3 minus is a diamagnetic. This is apparent anomaly is explained by the valence bond theory in terms of formulation of inner orbital and outer orbital coordination entities. MnCn6 3 minus, FeCn6 3 minus and C2O4 3 minus are inner orbitals complexes involving D2sp3 hybridization. The former two complexes are paramagnetic and the later diamagnetic. On the other hand, MnCl6 3 minus, FeF6 3 minus and COF6 3 minus are outer orbital complexes involving sp3d2 hybridization. They are paramagnetic corresponding to 4, 5 and 4 unpaired electrons. 5.5.3 Limitation of valence bond theory. Will the valence bond theory to a larger extent explains the formulation of structures and magnetic behavior of coordination compounds. It suffers from the following shortcomings. It involves a number of assumptions. It does not give quantitative interpretation of magnetic data. Third, it does not explain the color exhibited by coordination compounds. Fourth, it does not give a quantitative interpretation of thermodynamic or kinetic establishes of coordination compounds. Fifth, it does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. It does not distinguish between weak and strong ligands. 5.5.4 Crystal field theory. The crystal field theory (CFT) is an electrostatic model which considers the metal ligand bond to ionic arising purely from electrostatic interactions between the metal ion and the ligand. Ligands are treated as a point charges as in case of anions or point dipoles in case of neutral molecules. The 5d orbitals in an isolated case as metal ion have same energy, that is, they are degenerate. This degeneracy is maintained if a spherically symmetric field of negative charges surrounds the metal atom ion. However, when this negative field is due to ligands, either anions or the negative ends of bidipolar molecules like NH3 and H2O in a complex, it becomes asymmetrical and the degeneracy of d orbital is lifted. It results in the splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal field. Let us explain the splitting in different crystal fields. A. Crystal field splitting in octahedral coordination entities. In octahedral coordination entity with 6 ligands surrounding the metal atom ion, there will be repulsion between the electrons in metal d orbitals and the electrons or negative charges of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, dx2 y2 and dz square orbitals which point towards the axis along the direction of the ligand will experience more repulsion and will be raised energy, and the dxy, dyz and dxz orbitals which are directed between the axes will be lowered in energy relative to the average energy in the spherical crystal field. Thus, degeneracy of d orbitals has been removed due to ligand metal electron repulsions in the octahedral complexes to yield 3 orbitals of lower energy, T2G set, and 2 orbitals of higher energy, EG set. This splitting of the degenerate level due to presence of ligand in a definite geometry is termed as crystal field splitting, and energy separation is denoted by del naught. The subscript O is for octahedral. Figure 5.8. Thus, the energy of the 2 EG orbitals will increase 3 by 5 del naught, and that of 3 to G will decrease by 2 by 5 del naught. The crystal field splitting del naught depends upon the field produced by the ligand and the charges on the metal ion. Some ligands are able to produce strong fields in which case the splitting will be large, whereas others produce weak fields and consequently result in a small splitting of d orbitals. In general, a ligand can be arranged in a series in the order of increasing field strength as given: I minus, then Br minus, then SCN minus, then Cl minus, then S2 minus, then F minus, then OH minus, then C2O4 2 minus, then H2O, then NCS, then ED2 4 minus, NH3, then En, then Cn, then CO. Such a series is termed as a spectrochemical series It is an experimentally determined series based on the absorption of light by complexes with different ligands. Let us begin. Let us assign electrons in d orbitals of metal and in octahedral entities. Obviously, the single d electron occupies one of the lower energy T2G orbitals in D2 and D3 coordination entities. The d electrons occupy the T2G orbital singly in accordance with the Hund's rule. For d4 ions, the two possible patterns of electrons distribution arise. Fourth electron could either enter the T2G level and the pair with an existing electron. Second, it could avoid paying with the price of the pairing energy by occupying the EG level. Which of these possibilities occur depends on the relative magnitude of the crystal field splitting del naught and the pairing energy P. P represents the energy required for the electron pairing in a single orbital. The two options are del naught del P. The fourth electron enter one of the EG orbital, giving the configuration T3 to Tg Eg1. Ligands for which del naught are known as weak field ligands and form high spin complexes. Del naught greater than P, it becomes more energetically favorable for the fourth ligand to occupy a 2Tg orbital with configuration T2G4 Eg0 ligands, which produce this effect are known as strong field ligands and form low spin complexes. Calculations show that D4 to D7 coordination entities are more stable for strong field as compared to weak field cases. B. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity formation, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. For the same metal, the same ligand and the metal ligand distances, it can be shown as del T 4/9 del naught. Consequently, the orbital splitting energies are not sufficiently large for forcing pairing and therefore low spin configuration are rarely observed. The G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since tetrahedral complexes lack symmetry, G subscript is not used with energy levels. 5.5.5 Color in coordination compounds. In the previous unit, we learned that one of the most distinctive properties of transition metals complexes is their wide range of colors. This means that some of the visible spectrum is being removed from white light as it passes through the sample, so the light that emerges is no longer white. The color of the complex is complementary to that which is observed. The complementary color is the color of the generated from the wavelength left over. If green light is observed by the complex, it appears red. Gives the relationships of the different. Table 5.3 gives the relationship on different wavelength absorbed and the color observed. The color in the coordination compounds can be readily explained in terms of crystal field theory. Consider, for example, the complex TiS2O whole 6 3 plus, which is violet in color. This is an octahedral complex where the single electron Ti3 plus is a 3D1 system and the metal d orbital is in the T2G level in the ground state of the complex. The next higher state available for the electron is the simply EG level. If the light corresponding to the EG energy of blue-green region is absorbed by the complex, it would excite the electron from T2G level to EG level, T2G1 EG0, T2G0 EG1. Consequently, the complex appears violent in color. For example, 5.1.0, the crystal field theory attributes the color of the coordination compounds to the transition of the electron. It is important to note that in the absence of ligand, crystal field splitting does not occur, and hence the substance is colorless. For example, removal of water from TiS2O whole 6 Cl3 ionetic renders it colorless. Similarly, anhydrous copper SO4 is white, but copper SO4.5H2O is blue in color. The influence of the ligand on the color of complex may be illustrated by considering the NiS2O whole 6 2 plus complex. which forms when nickel 2 chloride is dissolved in water. If the dedentate ligand ethane 1 to diamine is progressively added in the molar ratios Ni 1:1, 2:1, 3:1, the following series of reactions and their associated color changes occur. NiH2O 6:2 plus NiH2O Cn2 plus gives 2H2O pale blue. NiH2O whole 4 En2 plus En NiH2O En2 plus 2H2O blue purple violet. Colors of some gemstones. The colors produced by electronic transitions within the d orbitals of a transition metal ion occur frequently in everyday life. Ruby is aluminium oxide Al2O3 containing 0.5 to 1% Cr3 plus ions D3, which are randomly distributed in position normally occupied by Al3 plus ion. We may view this chromium 3 species as octahedral chromium 3 thrice complexes incorporated into the alumina lattice. DD transition at these centers give rise to the color. In emerald, figure 5.2b, Cr3 plus ion occupy octahedral sites in the mineral beryl B3L2 SiO18. The absorption bands seen in the ruby shift to the longer wavelength, namely yellow, red, and blue, causing emerald to transit light in the green region. A. Ruby. This gemstone was fauna in marble from Mogok, Myanmar. B. Emerald. This stone was found in Mozo, Colombia. 5.5.6 Limitation of crystal field theory. The crystal field model is successful in explaining the formation, structure, color, and magnetic properties of coordination compounds to a large extent. However, from the assumption that ligands are point charges, it follows the anionic ligand should exert the greatest splitting effect. The anionic ligand actually are found at the low end of the spectrochemical series. Further, it does not take into account the covalent character of bonding between the ligand and the central atom. These are some of the weaknesses of CFT, which are explained by ligand field theory and the molecular orbital theory, which are beyond the scope of the present study. 5.6 Bonding in metal carbonyls. The homoleptic carbonyls, compounds containing carbonyl ligands, are found by the most transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel 0 is tetrahedral. Polycarbonyl iron 0 is trigonal bipyramidal, while hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of 2 square pyramidal MnCO whole 5 units joined by Mn bond. Octacarbonyl dicobalt has a CO-CO bond bridged by 2 CO groups. The metal carbon bond in metal carbonyls possesses sigma and pi character. MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbitals of the metal. The MC pi bond is formed by the donation of a pair of electrons formed a field d orbital of a metal into the vacant anti-bonding orbital of the carbon monoxide. The metal to ligand bonding creates a synergic effect which straightens the bond between CO and metal. Importance and application of coordination compounds. The coordination compounds are of great importance. These compounds are widely present in mineral, plant, and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgy, biological systems, industry, and medicine. These are described below. Coordination compounds find use in many qualitative and quantitative chemical analysis. The familiar color reactions given by metal ions with a number of ligands, especially selecting ligands, As a result of formation of coordination entities form the basis of their detection and estimation of classical and instrumental methods of analysis. Examples of such reagents include EDTA, DMG, dimethylglycosine, alpha-nitroso, beta-naphthenol, cupron, etc. Hardness of water is estimated by simple titration with Na2-EDTA. Hardness of water is estimated by simple titration with Na2-EDTA. The Ca2 plus and Mg2 plus ions form stable complexes with EDTA. The selective estimation of these ions can be done due to differences in the stability of constant of calcium and magnesium complexes. There are some important extraction processes of metals like those of silver and gold make use of the complex formation. Gold, for example, combines with cyanide in the presence of oxygen and water to form coordination entity AuCN2 in aqueous solution. Gold can be separated in metallic form from this solution by addition of zinc. Similarly, purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. For example, impure nickel is converted to NiCO4, which is decomposed to yield pure nickel. Coordination compounds are of great importance in biological systems. The pigment responsible for photosynthesis, chlorophyll, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood which acts as an oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the compound of iron, the pernicious anemia factor, is a coordination compound of cobalt. Among the other compounds of biological importance with a coordinated metal atoms are the enzymes like carboxypeptidase and a carbonic anhydrase, catalyst of biological system. Coordination compounds are used as catalysts for many industrial processes. For example, include rhodium complex, PS3P3 RSCl, Wilkinson catalyst used for the hydrogenation of alkenes. Articles can be electroplated with silver and gold much more smoothly and even from solutions of the complexes. AgCN2 and AuCN2 then form a solution of simple metal ions. In black and white photography, the developed film is fixed by washing with hypo solution, which dissolves the undecomposed HBr to form a complex ion AgS2O3 whole twice 3-. There is a growing interest in the use of chelate therapy in medicinal chemistry. An example is the treatment of problems caused by presence of metals in toxic proportions in plants and animal systems. Thus, excess of copper and iron are removed by chelating ligands. D-penicillin amine and desferoxamine B with the formation of coordination compounds. EDTA is used in the treatment of lead poisoning. Some compounds of platinum effectively inhibit the growth of tumors. Examples: cisplatin and related compounds. Summary: the chemistry of coordination compound is an important and challenging area of modern inorganic chemistry. Due to the last 50 years, advances in this area have provided development of new concepts and models of bonding and molecular structure and novel breakthroughs in chemical industry and the vital insights into the function of critical compounds of biological systems. The first symmetric attempt at explaining the formation, reaction structure and bonding of a coordination compound was made by Alfred Werner. His theory postulated the use of two types of linkages, primary and secondary, by a metal ion in a coordination compound. In the modern languages of chemistry, these linkages are recognized as the possible ionic and non-ionizable bonds respectively. Using the property of isomerism, Werner predicted the geometrical shapes of a large number of coordination entities. The valence bond theory explains the reasonable success and formation, magnetic behavior and geometrical shapes of coordination compounds. It, however, fails to provide a quantitative interpretation of magnetic behavior and has nothing to say about the optical properties of this compound. The crystal fit theory (CFT) to coordination compounds is based on the effect of different crystal fields provided by the ligand taken as point charges. On the degeneracy of d orbital energies of the central atom ion, the spreading of the d orbitals provided different electronic arrangements in strong and weak crystal fields. The treatment provides for the quantitative estimation of orbital separation energies, magnetic moments, and spectral and stability of parameters. However, the assumptions that ligands constitute point charges creates many theoretical difficulties. Many carbon bond in metal carbonyls possesses sigma and pi character. The ligand to metal is sigma bond and metal to ligand is pi bond. This unique synergic bonding provides stability to metal carbonyls. Coordination compounds are of great importance. These compounds provide critical insights into functioning structure of vital components or components of biological systems. Coordination compounds are also find extensive application in metal. All for this video, guys. This was the chapter. I hope you have revised it, and soon you will see the complete explanation of this chapter in our channel. See you soon. I wish you all the best for all your challenges in life. All the best.